So, good afternoon, everyone. Welcome to this last lecture in our mini school on machine learning for high energy physics. And this afternoon, we are very lucky to have Professor Bruce Mellado with us from the University of Witwatersrand and ITEMBA Labs. And he will give us the final overview to show us how all the lectures that you had before can be joined together in also in the understanding of the use and role of big data, machine learning in physics in general, and more specifically in high energy physics, where I think the examples will come from. Yeah. So Bruce, we are really happy that you are with us for the grand finale of the mini school. So you're already sharing your screen. You're welcome to start with your presentation. Just a last reminder that I always forget to do to the participants to please make use of the Q&A facility to ask questions, or maybe if we have time later to raise your hand. And Dr. Sinaisky, who joined us while we were chatting, will also help us moderate the questions so that Bruce doesn't have to stress with observing the chat and the Q&A while he's talking. Yeah. So Bruce, thank you very much for being with us today. And the floor is all yours. Thank you.
Thanks a lot, Francesco, for the great presentation. And yes, this is going to be the finale of the mini school in big data and machine learning in particle physics. So we talk a lot about big data. So what I'm going to try to do today is to introduce what big data really is in practice and what is not, because there's a lot of misconceptions about what big data is. And then once I'm done with that, I will later introduce the subject in an actual concrete context of particle physics, and I will link it up with machine learning. All right, so the first thing I'm going to do is I'm going to give a grand view of what the big data problem is, mostly by addressing what big data is not. Let me time myself, sorry. Then I will give a physics question that was posed or is posed to scientists that drives the technological challenge that creates the big data problem. And I will explain what is the big data challenge based on what I had said before. And then I will link it up with AI so that you can connect the big data problem with the concepts that have been introduced by Professor Carr and Dr. Ruan. And if I have time, depending on how it goes, I'll give a couple of examples of how relatively sophisticated machine learning techniques and methodologies can be used when big data and these techniques are coupled to solve a practical problem. All right, so let's get started. So let's first clear some misconceptions, because the very same title and notion of big data includes big, and that is very, very confusing, because the reality is that big data does not necessarily mean a huge cloud computing with a huge amount of data and you're running massive amount of jobs and loops on a huge amount of data. In fact, that's not what the core of big data is. In terms of how big data manifests itself, is more about the large multiplicity of data volumes and formats. Big data basically includes a large number of large different types of data formats and volumes within it, with a tendency of reducing data sets and reducing data flows. So the role of big data in practice is not for you to be provided with infrastructure to run massive amount of jobs that takes weeks or years to run, but rather to embed intelligence in how you organize the data to go from very big data sets to something that is significantly smaller, that a user can extract information from using a terminal or even a laptop. So that's the kind of intelligence that big data implies. So it sounds like very big, but in reality, the intention is actually quite different. Also, it doesn't have to be made of digital data and zeros and ones. It can also be analog signals. In fact, analog signals is a part of the big data problem, As a matter of fact, most of the data in the world is in fact analog. Not every piece of data that we generate in the world is digitized. So analog signals, which are basically currents and voltages, are also a part of that big data problem. Big data is not about very high throughputs. It's really, in the end of the day, it's about developing the tools and the infrastructure and the intelligence so that the user can perform advanced analytics on small data sets, from very large data sets to small data sets. And the intelligence that that entails is about being able to pick the relevant information and sufficient information. And we're not talking about metadata here, it's more complex than that. That will allow you to survey a very big data set through a small data sets. And here comes, of course, the notion of multiplicity of volumes and multiplicity of formats. Now, sometimes big data is also confused with cloud computing. Now, cloud computing is a part of the big data problem. And as you will see in a minute, in fact, it's a very small part of the big data problem. So however big the cloud computing is, or the cloud computing of the giants like Google or IBM is, the big data problem is significantly bigger than that. And the cloud computing is just a part of it. In fact, is the end point of the big data problem. Once you have decided to store and keep the data you think is sufficient for you to sample this big data problem, then you can go to computers, and after that you can do what we call offline processing. But that is the end of the big data problem. That's the end point of the big data problem. Okay, so we should not confuse big data with computing or high performance computing. As a matter of fact, as you will see in the next slide, much of the signal processing in the world, in fact, happens real time, before even the cloud is participating in data flows or even in processing. Sometimes processing happens with purely analog signals. So the cloud computing, if you think about it, is, yes, it's becoming massive. Now people talk about exascale systems and whatnot, but that yet remains a tiny fraction of all the data that we generate. So what one can say, and safely, that computing is really the tip of the iceberg of the big data problem. The big data problem starts earlier than that, and the big data problem includes all the steps from generation to final processing and all the way to the small formats that I just discussed. And I will be concreting what I mean by small formats in the context of particle physics. All right, so before I go to give a definition, let's look at this graph here, which is particularly important, and as it depicts what the problem of computing is. This has not been updated, but the qualitative features of this graph still remains in the last decades. What you see there in blue is the ability with current technologies to store, where blue is the ability to compute. Okay, and these are basic classical computers. Of course, there is obviously the quantum revolution that is coming and will create quite a stir here. But let's just stick to this problem at the moment. Let's to what we have today. And the problem we have in computing in general is that our ability to store far lags behind our ability to compute, and our ability to compute is far behind our ability to produce data. So there's a huge gap between our ability to store, and therefore cloud computing is just the tip of the iceberg. So what actually happens in real life, what happens in practice, is the fact that we are selecting only a fraction of the data that constitutes the big data problem in the world, whether it is in science or elsewhere, okay? And this has to do with the fact that our ability to store is actually severely lagging behind everything else, okay? This is a very important consideration. The situation hasn't changed in the past decade or so. All right, so let me give a view or a definition that will fit well into what I'm going to say later. Of course, computer scientists can give different definitions as well, and I don't think there is the one definition of the big data problem. So I'm going to give a definition that is going to help us deal with a problem if in big science. So that's what this definition is going to be cater for, taking into account what I said earlier already. So let's read from the box. The big data problem is the processing of large amounts of analog and digital signals leading to a reduced amount of data that is distributed for analysis and synthesis. Okay, so this definition basically is a compact way of saying everything that I said earlier. First, that the big data problem is not just digital, it could be analog. It includes processing, which could be massive, but in the end of the day, with the role of big data is to reduce the data we're going to eventually analyze to extract information to a much smaller size or a much smaller data format. So that's really the definition is basically in a condensed way talking about all these features that big data in practice is about in big sciences. And the context that I'm introducing it is big sciences being the Large Hadron Collider, the big science question that I will be talking about in a minute. And when I talk about analysis, is basically the analysis is about breaking down the data into a smaller components to understand it, and then synthesis is to basically bring all those pieces together to say, this is what I have learned about the data. This is the insight that I have received from this analysis, and this is what I've learned from it, where I merge the practical information from the data with the existing theoretical knowledge. That's what I mean by synthesis, okay? And synthesis is basically writing a paper, if you think about it, drawing a conclusion about what I've learned from the data. All right, so let's go to the physics question, to the big physics question, as our team is composed of particle physicists. So in order to deal with particle theory physics in general, it's important to discuss distance, because for every distance we have a type of physics or a particular discipline within physics, whether it is atomic, condensed, biophysics, astrophysics, cosmology. But what happens is that as we become more and more sophisticated and push the boundaries, when we go to large distances, we push the boundaries with large distances, and the SKA will be the large scale frontier, if you think about it. And when we increase energy and we increase the amount of energy we inject in a very small amount of space, we actually are creating microscopes. We go to smaller and smaller distances. We try to go to distances much smaller than that of a nucleus. And that's what particle physics does. And that's what the Large Hadron Collider is. So the Large Hadron Collider is the biggest microscope that deals with the smallest possible distances. By contrast, we have the SKA being the large scale frontier. Now, what happens in reality, even though we sort of seem to diverge in terms of what distances we probe, the reality is that both the SKA and the Large Hadron Collider are dealing with a very, very similar questions, or even the same question: what is the origin of mass in the universe? Okay, despite the fact that they seem to have converged through because of our instrumentation, because of the distances we study, where the physics that underlies that effort is really meeting in somewhere in the middle when we talk about the origin of mass. In particle physics, we talk about the Higgs boson, which is the particle that provides mass to known elementary particles. But on the other hand, we know that the universe is made of unknown matter. And most of the matter in the universe, which we know from gravitational patterns, which we know exists, we don't know what it's made of, what its spectroscopy is, how those particles interact with each other than gravitationally, of course, and how these particles, in fact, talk, or if they talk at all, with the matter that we can smell and touch. So that is really all put together within the context of the origin of mass. And the LHC and the SKA, in fact, deal with the same fundamental question. So this is how interconnected we are, despite the fact that we are looking at very different distances. Okay, so let me look at the Large Hadron Collider. So what the Large Hadron Collider is, so it's the biggest microscope ever put together. Why? So you put together a bunch of magnets and underground. It's about 100 meters below Earth to shield the system from cosmic rays. This accelerator has a bunch of magnets that will force protons to go in a circular trajectory instead of a straight line. And protons will be accelerated through a series of pre-accelerator complexes and also RF cavities in the actual LHC. And then they are kept in orbit. They are kept in clouds for a long time, typically 10 hours or more, so that all these collisions are recorded by the experiments. These experiments are, you can think of them as very complicated cameras with a lot of channels, and that's the source of the big data problem. But I will talk about that later. And the discoverers of the Higgs boson were the ATLAS and the CMS experiment. But South Africa contributed and contributes to ATLAS, but also to the ALICE experiment here. There's also a big community in South Africa working on it. All right, so why the big data challenge? Why the Large Hadron Collider and discover the Higgs boson became already in the 80s the quintessential big data problem? Remember, these are mega projects that take decades to build. The Large Hadron Collider was conceived in the 80s, and it was concluded in the 2000s, and it started taking data in 2010. So imagine the span, and back then the computing capabilities were actually meager compared to what we have today, and yet people had to think about huge data flows that we have today. So that is, in our field, the quintessential big data problem. So I've already showed this slide, and this is a different view. It's a bit flashier with emphasis on what South Africa does at CERN, contributing to ALICE, ATLAS, the solved experiment, and also a theory component. And what we essentially do is accelerate the physicists, pump protons from hydrogens, they repopulate the electrons from atoms of hydrogens, then the protons are accelerated through different pre-accelerator complexes that are pumped into the Large Hadron Collider in the form of clouds, and then those clouds go through each other. And as those clouds go to each other, you basically, through each other, you have a certain probability that protons will collide head-on. That's basically what collider particle physics does from the accelerator side. And as we know, protons are composite particles that are, meaning that they have a structure. A proton is not an elementary particle. It has structure in that it has quarks and gluons and whatnot. So as the two protons go through each other and collide head-on, what you do is partons interact through fundamental interactions, and the Higgs is produced. Needless to say, this is an extremely rare occurrence. That's why we have to produce insane quantities of data to find a handful of Higgs events. That was done. That is what was done for discovering the Higgs boson in 2012. Now the challenge comes here, and now I'm walking towards the challenge. So because we are looking at smaller and smaller distances and processes that are more and more rare, what we have to do in collider particle physics is to collide particles more and more often with higher and higher frequency. So the LEP accelerator that collided electrons and positrons that started taking data in '89, and they stopped early 2000s, they were colliding every 22 microseconds, or a crossing rate of 30 kilohertz, which at the time was something absolutely fantastic. Then came the Tevatron, the proton-antiproton machine in Chicago, that started its run one with a crossing rate of almost 300 kilohertz, or collisions every 3.5 microseconds. So you basically now narrow the time between collisions. Why? Because you need to look at more and more rare processes. For that, you have to collide particles more and more often. Then the Tevatron run one was upgraded to run two, where the collision rate went down from 3.5 microseconds to a staggering almost 400 nanoseconds. That's a very small amount of time, leading to a crossing rate of 2.5 megahertz, 2.5 million times a second. So you collide things 2.5 million times a second. That's already, you know, mind-boggling. But the Large Hadron Collider came to beat that even further, in that the collision rate, or the bunch crossing at the LHC is now down to 25 nanoseconds. That's our operating bunch crossing, and the corresponding crossing rate is 40 megahertz, meaning that we collide protons 40 million times a second. We take pictures in those detectors 40 million times a second. So you can already understand what it is we're talking about here. If you have a detector that speeds, which is very complex, and it has hundreds of millions of channels, and you have those hundreds of millions of channels taking pictures 40 million times a second, so you kind of start imagining what kind of problem we're dealing with. So in order to deal with this problem, we developed in particle physics a concept called triggering. And this is what I was alluding to earlier. The big data does not necessarily start with digital data. In fact, most of the data, the Large Hadron Collider, up until the late 20s, is analog data. Okay, and the absolute 99.999% of all the data is analog. We only digitize a tiny fraction of the data. So in order to be able to make a decision as to what data is interesting to us, we devise what we call multi-level trigger systems. Each level performs a particular type of computations. Level 1 is purely hardware, so it only deals with analog signals, and is there to reduce the rate of data to something that can be dealt in by a digital system, which is the role of level 1. That level 1 will lead to level 2, and then level 2 will lead to a level 3 type of computation, where you now have computers, where computers can come in. They are fast enough in order to come in and do computations. Computers are, in fact, in general, off-the-shelf computers have very poor latencies. In fact, they're very slow, as a matter of fact. So you really have to do things that allow you to do decisions essentially within microseconds. And that is something that a regular computer can simply do. So computers come in later when you have latencies of order of seconds or a fraction of a second. Mm-hmm. All right, so in terms of the schedule, you see here that big projects like the SKA or the Large Hadron Collider entail many, many years of operation. This is there's a major investments. You want, tens of thousands of PhDs to come out of it, a lot of tech transfer, a lot of innovation coming out of it, because it's a huge investment. So it really spans decades. So as I said earlier, we started taking data in 2010, the last operation, or the shutdown of the Large Hadron Collider, is not foreseen till the end of the 30s, maybe early 40s. So we know that the last PhD student that will be writing his or her thesis on the last Large Hadron Collider data hasn't been born yet. So that's really the span of the operation, and it undergoes a lot of upgrades. Okay, we have a certain configuration. Those configurations are upgraded and improved. Maintenance is also performed, and so on and so forth. Now, I think I'm going to skip this. So let me go to the computing chart. So we said that there's a triggering system. Right now, our triggers are mostly analog, and then you need to make decisions within essentially microseconds, and regular computers cannot do that. Computers need more time to make decisions. Now, once you are past that stage, you basically now are ready to transfer data to computers. So this is really why we refer to the computing model and cloud computing as the tip of the iceberg of the big data problem. Okay, you need to do a lot of work, and it's a massive amount of work and design and whatnot that happens in order for scientists to choose which is the correct data to pick, because if you don't do it correctly, that data is gone for good. The SKJ, in fact, faces a very similar problem when it comes to correlating the signals from different antennas. Okay, you have to be extremely smart so that you don't lose the data, because you cannot keep. I mean, we cannot create systems modern systems in big sciences where we store all the data in computers, we later take a look at it, and then if we don't like it, we discard it. We don't have a luxury because we can't store the data, as I showed you earlier. The challenge in computing it revolves around the fact that we cannot store as much data as we produce, not even close to a tiny fraction to the data we produce. So the computing challenge comes at the end. So when we say computing challenge, we're talking about the end of a long chain. Okay, so to recap here, we have a detector that sits underground, and from the right and from the left, protons come in, protons collide, and the debris are, so to say, going to the detector, and the detector takes pictures 40 million times a second, and that creates data flows of petabytes per second. So even today, 30 years after, or even almost 40 years after the LHC was conceived, we cannot handle that data. So it's clear that you have a triggering system to reduce those data flows to something that is more amenable to computing models of today. And that is a few hundred megabytes per second. So you have to make this extraordinary effort, this extraordinary big data effort to pick the only interesting data out of a petabyte down to hundreds of megabytes per second. This is what we can handle with today's computing systems. And that data is first stored at CERN. I will talk about the computing model of the Large Hadron Collider, the WLCG. And then it will be distributed worldwide because the community is made of thousands of people from all over the world, including the Southern Hemisphere and South Africa. So everybody has to see the data. So it has to be distributed in a way that is smart. And that's what the computing challenge is all about. Is once you have chosen the data you can store, you further reduce those data formats so that a researcher, from student all the way to a senior researcher, can go to a computer or even a terminal or a laptop and draw a physics conclusion and write papers. Okay, so imagine the amount of work that the big data problem entails from the moment we generate the data to the moment where someone opens a terminal and visualizes a tiny fraction of interesting data. All right, so what is the WLCG, or the Worldwide LHC Computing Model, or GRID as we call it, which is also referred to outside the field as cloud computing. So because the data comes from one point, which is CERN, so the accelerator sits at CERN, the computing model is sort of like CERN-centric, it's hierarchical, okay? It's evolving away from that model, but that's really the baseline of what the LCG is. So you have the data stemming from the experiments. They're going to huge computer centers at CERN. Now which is called TR0. Now the TR0 is distributed. We have a TR0 in Geneva, Switzerland, and another TR0 in Budapest, in Hungary. And then surrounding, in terms of the computing model, TR0s are TR1s, which are also quite massive computing farms that typically sit in big countries of Europe and the US, typically. And then surrounding this distributed Tier1 system, we have a very large amount, now hundreds of Tier2 sites, and South Africa is really one of them. And it's hierarchical in the sense that each tier, whether it's Tier0, Tier1, or Tier2, they have assigned a number of tasks that are distinct from each other. And that has to do with a complex optimization of resources. But in the end of the day, the idea of the system, there's a middleware that sits that harnesses the data and connects all these sites. The endpoint is that the user is able to retrieve any kind of data from the experiment at any given time. So I think I'm going to skip this. In terms of the geolocation, you can see here a map up until 2017, but things haven't changed so much. So as I said earlier, you have in the stars are the Tier0s in Geneva and in Budapest in Hungary. Then you have the green, which are the tier 1 sites, which are of course all in the Northern Hemisphere. And then the blue dots, or the blue signs here, pertain to tier 2 facilities, of which there's few of them in the Southern Hemisphere, and we have one at the CHPC in Cape Town. Right, so I'm just going to wave my hands here because this is obviously a very complex question technically. Just to introduce the concept of middleware. The middleware is a particular type of software that is basically, if you wish, the infrastructure of this grid, the infrastructure of this cloud computing, which allows for the integration of all these sites and the movement of data, the backup of data, and the cataloging of this massive amount of data with so many different types of formats, as I said in the very beginning, with different sizes. And that is really, so to say, what really runs this massive worldwide infrastructure, which sometimes is also called cloud computing. And it's something to have in mind, because what happens is that when the user, the physicist, interacts with the grid, he or she is barred from this complexity. He or she only needs to write a script, or sometimes few lines, to retrieve a particular type of data, and then the data is retrieved to your computer or your tier 2, where the tier 2 facility that is closest to you. And there's a lot of stuff that happens in between for that movement of data to be done reliably. Now, in terms of data formats, even though the actual digitized data that go into computers is tiny compared to all the data that we generate, because it's still so big, and we still have to differentiate different types to perform different functions. Because even though the data is tiny compared to everything, to the petabyte that we generate, we're basically looking at a very large amount of terabytes and petabytes of data, which is of course something that makes no sense for the user to dive into. And again, the role, as I said, the role of the big data is not to brute force yourself into a huge data set, is to embed sufficient intelligence in your analytics so that you look at only a small fraction of the data that is relevant from that huge amount of data you've generated. And this is really why as the computing model of the LHC was evolving, and I'm talking about the 2000s, before we started taking data, and also in the 2010s, we're basically generating ideas as to how most efficiently create these data formats, all the way from the raw data to more very high level types of data that allows people to understand and classify the complex phase space of the Large Hadron Collider. And you can see here is just an example of the size of the data format per proton-proton collision, or we call it event, from the raw data to the tag data. The tag data is closer to metadata, but not quite. And the balance between them is something that a physicist has to play with in order to be able to arrive at the right answer. Now, in terms of the computing model I just described earlier, the way the cloud computing model was conceived at the Large Hadron Collider was CERN-centric, was hierarchical, with a tier 0, tier 1, tier 2s, and then tier 3s, which is us with a computer connecting to the tier 2s. And that's how basically it started. Now, people realize that although that system has a lot of advantages, there's a lot you can do in terms of the efficiency of the system and utilizing resources fully by allowing more democratic and more horizontal connections between tier 1s, tier 2s, between tier 1s and tier 2s, and so on and so forth, which of course adds complexity to the interaction between the different stakeholders in this cloud system, but allows for the system to be more fully utilized and to be more efficient. So that's really the evolution. We go from a hierarchical system to a more mesh, M-E-S-H, not mess with two S's. It's not a mess, it's a mesh of computing systems with more complex interconnections that include more horizontal and more democratic communications. And of course, this entails a fast growth of the of computing resources in terms of CPU and also storage. Even though this is tiny, it basically we're looking at going from tens of petabytes in the beginning to now hundreds of petabytes of data to be stored. So basically, the notion of exabyte systems is coming about. Being that exabyte only a tiny fraction of what was really generated, and of course now we are now planning the start of the restart of the Large Hadron Collider in 2022, and there's a lot of debate about the funding options and the funding models to cope with such an increase in the computing model in terms of resources. All right, so that I think this is about half an hour. So I'm gonna touch upon basic notions in AI that were introduced by Professor Carr and were elaborated on by Dr. Ruan in terms of machine learning. And I will give you some examples of how this symbiosis and how this synergy between big data and machine learning comes about in order to solve a concrete problem, say the discovery of the Higgs boson. So, and it's important to have this in mind in that, the machine learning algorithms and methodologies sit on top a huge big data problem that is a precondition for machine learning to come in. So you should view machine learning as, so to say, if you wish, the cherry on top of this very long process of processing and organization of data that I just explained that comprises the big data problem. However, it's very difficult to decouple machine learning for the big data problem when we look at big sciences, being the LHC or the SKA epitomes of these systems. All right, so what we've learned so far about what machine learning is basically the ability of computing systems and algorithms to learn from the data that you feed to them. Now, what is very important to realize here, that this is not something isolated from the big data problem. You always have to have that in mind when you solve the problem, because you need to understand what it is you're missing and why. And second, this is not a black box, okay? This is absolutely essential, and this is really absolutely pivotal for anyone that wants to do machine learning or data science or big sciences, that machine learning is something that the scientist controls. This notion about artificial intelligence taken up from people, that's fine in science fiction movies and novels. But in reality, the scientist controls the machine learning process, and very much so, okay? So you should not think about a neural network as a black box that sits on top of something. There is a reason why machine learning is used, and there is a way to control machine learning. There's many different methodologies and tricks that we have in data science to actually do so. So the idea is that you basically train an algorithm on data, and then you test it on some independent data that was not used for training, and then you create predictions, and then you go back and forth in a cycle to really make sure that the machine learning is doing what you expected the machine learning to do, okay? The last thing you want to do is to just run a machine learning algorithm and then expect that it will just work for you the first time around. That never happens. That's not how machine learning actually works. It's an iterative process, and this is the reason for this cycle that we've got here. And this cycle can be quite cumbersome because the reality is that you really need to control what's inside the box, okay? And that's the reason why we had to do this in many iterations. In fact, for those that are interested, there is a very powerful website at CERN, which is an amazing resource for people that want to get acquainted with the state of the art of how artificial intelligence and machine learning is applied on the big data problem in the context of particle physics. But not only, even if you are not a particle physicist, you're going to find this information, this software, these platforms, and these frameworks very, very useful for your science and your applications. And this is all open source. This is actually one of the great things about machine learning, is that the algorithms are open source and free. And to me, that's really one of the big victories of scientific exchange, is that we don't believe in proprietary software when it comes to the core function of our analysis. And you have the link, and I strongly encourage you to go through it. Today, machine learning is quite sophisticated. Even though from the computer science standpoint, it's been around for decades, and the basic ideas stem from the 60s already. The integration of these techniques in software systems and software platforms has exploded in recent 5 years, and the adoption of more complex and more sophisticated machine learning techniques is something that has happened fairly recently. Even though we've been using machine learning for decades in particle physics, we've always used it, as you will see in a minute, for a particular type of applications. Now, especially since, for the past 5 years or so, the ways and the applications of machine learning intertwined with the big data has just exploded. It's really an amazing and fascinating field. And this is just a snapshot of what's actually happening. So when people go to CERN or work with us, they really get acquainted with a very wide range of machine learning algorithms and methodologies. So before I go to a couple of examples here, it's very important, for the point of view of conceptualizing the problem, before you run an algorithm, you have to really conceptualize the problem. And that's a condition sine qua non. We cannot just run an algorithm and just like that. You have to really understand what kind of methodology is applicable to solving your problem. What kind of information you have? What are the shortcomings of your information? What are the uncertainties of the information you have? And based on that, you make a choice of what kind of methodology you apply. And there is four main, sometimes, computer scientists talk about more, but let me just succinctly describe them. First of all is supervised learning, which is a fully labeled problem. I will introduce it later, where you know very well what you are classifying. Okay, you know that you're classifying the Higgs boson away from backgrounds. And that's the methodology that has been used for decades in particle physics, where we were looking for something we knew how it looks like. And the Higgs boson is the last prediction or fundamental prediction from the standard model. Therefore, we use supervised learning. We knew what we were looking for. And that's the type of things you use and the type of methodology you use if you know what you're looking for. Now, because we discovered the Higgs boson, and now what we're doing is we're learning from the data to get guidance as to how the standard model will break down, because we know it has to break down, and which discoveries are going to come after. Since we don't have clear guidance from theory, we now have to learn more and more from data. So what you do is you basically walk away from supervised learning towards unsupervised learning. And there is, of course, the notion of unsupervised learning, which is basically, I don't assume anything. I don't know what the data is made of. I'm trying to use machine learning to find correlations and find information. And then in between, there's the weak or semi-supervision, which basically tries to find a balance between a fully unlabeled problem and a fully labeled problem, which is also very useful, and I will talk about it in a minute if I have time. There's also reinforcement learning, and there's also some other type of classification. But when it comes to searching for new physics, you are basically really talking about somewhere between supervised and unsupervised learning going through weak supervision. The machine learning started, as I said, at the Large Hadron Collider. We were actually the first team back in 2002, excuse me, to introduce supervised learning in the search for the Higgs boson at the LHC. And that was already almost 20 years ago. And as I said, this was a shallow neural network at the time. We were not thinking about deep training yet. And it was a fully labeled classification problem where you have the Higgs and your background, and you want to separate them as much as possible. That's basically was the thinking. But things have evolved a lot, especially in the past 5 years, where we are now becoming more and more sophisticated and in terms of how deep the neural network is, in terms of how many variables we are used, what is the dimensionality of the problem, and the efficiency to reject backgrounds, where boosted decision trees were used in the past, very popular at the Large Hadron Collider, especially for the discovery of the Higgs boson almost 10 years ago, and also shallow neural networks. But you can actually, and there's of course a lot of mathematics underlying this, you can actually look at deep networks where you have a lot of hidden layers, and they're particularly powerful in dealing with problems with a lot more dimensionality. And you can see here the ROC curves that tell you that, you know, how effective these things are in order to suppress background when you go from a shallow network to a more deep network. And I'm going to close my talk with the notion of weak supervision. I already talked about it. The reason why do we have to walk away from full supervision and find a balance between full supervision and unsupervised learning is because we don't know exactly what we're looking for. And we now need to find ways of machine learning to help us find anomalies in the data. And I think, yeah, so I'm gonna close my presentation on this by illustrating how you can actually combine tools that were used for full supervision, but now in a different context, which we call weak or semi-supervision. And the idea is the following. You have a sample of data, huge amount of data, or a small amount of data, doesn't matter. These are the yellow tulips. And this is a sample that you know that does not contain new physics. It's all basically events in proto-proton collisions that are due to something you already understand, that you know belongs to the standard model, and that it is very interesting in its own right, but you really want to find deviations from the standard model. That's what really drives the field of particle physics today. And then you know that there is a sample there which can potentially have unknown new physics. And what you don't want to do now anymore is to do a fully supervised exercise where you have to make assumptions as to how and where is the red tulip. Okay, you know that there may be a red tulip, but you don't know exactly what it is, and you don't need to know exactly how it looks like. And by using the same algorithms, but in a different way, with a different organization of data, what you do now, instead of making a classification of full supervision between pure signal and pure background, what you're going to do is you're going to make a classification exercise between sample A and sample B, where sample B has an unknown mixture of new physics. So this is how we basically turn things around from a fully supervised exercise to something that is closer to unsupervised learning, which we call semi-supervision through classification exercises of mixed samples. And this is basically the direction that the field of particle physics is going towards by adopting more and more AI into the thinking, into the analytics, by using it to help us search for things that we don't have to have full knowledge of. And that's why machine learning is becoming so popular today, even much more so than it was 20 years ago, in that machine learning offers a tremendous amount of sophistication and tools that help us deal with this complicated problem. And I think that's basically it. I just want to leave some time for questions.
Thank you very much, Bruce, for this excellent journey of what's happening behind the scenes at the experiments at CERN. Thank you very much. I see that there are a few questions already in the Q&A, and I'm not sure if I should ask Xifeng or Ilya to guide us through the questions. Maybe one of them can volunteer.
Okay, I can read now. I can read it out. So Bruce Watson,
okay.
So it says, great characterization of the big data problem, Bruce. I had a student at LHC years ago, and the big data issue was evident then. Your graph of MIPS and disk speed hits the nail on the head. It would be nice to see data production rates on the same graph. I also like your yellow text box. Do you see any hope for planed old compression of this? Okay, so in terms of data flows, the data flows to the computing model is few hundred megabytes per second. It hasn't changed since then. I'm not sure I understand what plain old compression means in this context.
We can, Bruce, I can quickly give Bruce the permit to talk. So Bruce, if you would like to clarify your question, you're welcome to do so.
Thanks. This is other Bruce here. Thanks for your presentation, Bruce. By plain old compression, I meant, things like what's used in zip, these traditional old style Lempel ziv kind of algorithms, or run length encoding, algorithms that don't have deep insight into the nature of the data, but maybe are somehow simpler to implement, perhaps even in FPGAs for the kinds of data rates that you see at SK and the LHC.
Right. Thanks for the question. I think you frame it well, and I understand. So, I mean, currently, since the inception of the Large Hadron Collider, we've used compression techniques, standard compression techniques. That is part of the system, of course. But these compression techniques are not intertwined with say machine learning or anything like that. So they're fairly standalone. And in terms of the use of FPGAs, these are very, very popular today, and also for the upgrade of the Large Hadron Collider for the first step of the processing of the data. So in fact, most of the processing for the upgrade of the Large Hadron Collider, which will be operational late 20s, is going to be happening on FPGAs. That's really where the core of the processing will be. And we're going to be digitizing a lot more data with the upgrade compared to what we do now. Now we do a lot of analog processing, just basically thresholds, by applying thresholds on analog signals, and that's where most of the processing is happening. And then some processing is also happening on FPGAs. But now the use of FPGAs will be absolutely massive. I don't know if that answers, or at least partially, your questions.
Absolutely. Thanks very much. Also for a very nice talk.
Thank you. Well, I see Sean. Is it possible to use ANNs and CNN networks, the same use for OCR, to determine the missing force continued to physics trajectory by passing on forces in the network? Yes, the answer is yes. In fact, now the field is moving towards things like graph, deep learning systems like graph neural networks is now becoming very, it's being talked about. Of course, there is a lag between physicists writing papers and talking about applications to implementing that in the experiments. It takes a few years, but it's been demonstrated that especially graph neural networks are very powerful in doing these things. Now, obviously, you have different generations of people, different generations of scientists. So, the adoption obviously takes a lag compared to the conceptualization. But yeah, these ideas are on the table. That's a very good suggestion. Thanks, Sean.
Thank you, Bruce, for answering the question. Thank you very much. It looks like we don't have any more urgent questions, unless one of the participants wants to quickly raise a hand and ask it. If that is not the case, then Bruce, thank you so much for a very nice and motivating talk. Motivating in the sense to want to learn more, and I'm sure we will have many more mini schools on machine learning, artificial intelligence, and big data, and so on in the near future. So thank you very much, Bruce, to Dr. Ruan, and to your whole team, also the members that are not present today. And let me use this opportunity to announce the next mini school that will start next Tuesday. Yeah, and The school will be given by Professor Martin Bucher, who is also a NITheCS associate, although he's based in Paris, but he's affiliated with UKZN. And he will speak about exploring the cosmic microwave background radiation. Yeah, so we will go from the very small to the very big. Yeah, so I'm looking forward to see most of you again next week. And again, Bruce and your team, thank you very much. Ilya, thank you for joining us as well, and thank you to all the participants. So then I wish you a good afternoon, and I hope to see you again in large numbers next week. Thank you very much. Bye.